Thank you for tuning in. This is Lance, your host of Strange Bites, where we take real science and wrap it up in a creative story and serve it in 15 minutes or less. If you're enjoying the show, please hit that subscribe button on your favorite podcast app. Give me a follow on social media. And now, let's jump into the next bite. You're standing on a quiet stretch of northern Michigan farmland. The air smells like wet soil and diesel. In front of you is a steel wellhead. Nothing dramatic, just another gas well punched into the Antrim Shale. A black, organic-rich rock layer laid down 350 million years ago, when this part of the world was a shallow, oxygen-starved sea. Energy companies drill these wells, pump up water mixed with natural gas, strip out the methane, and move on. Most people never think twice about what else might be riding up in the water. But one day, a University of Michigan team did. They filtered hundreds of liters of that deep water. They stained it. They sequenced the DNA. They even tried to grow whatever was living in it on plates in the lab. What came back was not the usual handful of bacteria and archaea that the scientists expect in the deep subsurface. It was a whole hidden community. Hundreds of feet below the surface, between 650 and 640 feet down, an entire ecosystem of rock-eating fungi, microscopic animals, and parasites have been quietly thriving in total darkness for thousands of years. This is the story of how we found them, and what it means that they were there all along. This is episode 47, The Rock Eaters of the Antrim Shale. The Antrim Shale sits under much of the Great Lakes region. It's one of the older shale gas plays in the United States. Denovian-aged mud that turned into rock rich in ancient organic matter. The water that flows through its fractures is not surface rainwater. Isotope measurements show most of it last touched the atmosphere about 11,000 years ago, when the great ice sheets were melting at the end of the last ice age. Meltwater trickled down through the cracks and pores, carrying surface microbes with it. And then the system sealed itself off. For millennia, that water has been moving slowly through the dark, dissolving tiny bits of the shale's buried carbon. Scientists already knew about bacteria and methane making archaea living down there. What almost no one expected was complex life, eukaryotes in meaningful numbers. Quinn Moon, a doctoral student at the University of Michigan, led the work. Senior author Tim James, curator of fungi at the university's herbarium, oversaw the fungal side. They sampled 6 working gas wells. At each wellhead, they collected roughly 21 gallons of water, filtered it until the filters clogged, and went to work. Under the microscope, using a stain that lights up fungal cell walls, they counted between 4,200 and 6,800 fungal cells in every milliliter of water. A single drop held about 250 fungal cells, roughly the same density you'll find in a drop of ocean water. Scale that up, an entire Olympic-sized swimming pool of this subsurface water would contain more than 12 trillion fungal cells. Genetic sequencing revealed 689 different fungal species, or close equivalents. 13 of them appeared completely new to science. One strain, called Tychospora, matched its nearest known relative at only 74%, distant enough that it essentially is its own thing. The team managed to grow 205 pure cultures in the lab. Those cultures are now frozen and stored at the University of Michigan's herbarium as the first public collection of deep subsurface fungi. Many of the dominant fungi belong to groups we know from the surface as wood rotters, Agaricomycetes and Dothidiomycetes. On the surface, they break down lignin and cellulose, the tough structural molecules in plants. Down in the shale, they appear to be doing the same job on the ancient organic matter locked inside the rock. In other words, they're eating the shale itself. But the fungi were not alone. The same DNA sequences turned up genetic traces of rotifiers, those tiny wheel animals you sometimes see in pond water. Segmented worms, roundworms, and tardigrades, the famous water bears that can survive extremes that would kill almost anything else. There were also parasites, Ichthyosporia, that infect animals, and Roselomycota that attack other fungi. Put together, it looks like a real food web. Some organisms break down the rock carbon, others graze on the decomposers, still others parasitize the grazers. Predators, prey, and parasites all living in the dark hundreds of feet below Michigan farmland. The researchers are careful. Pumping water to the surface can introduce a little oxygen that may not exist at depth. Earlier studies of the Antrim already showed plenty of methane-producing microbes which prefer low oxygen conditions. So we still do not know exactly how these larger organisms get their energy or how active they are day to day. What we do know is that the chemical conditions have been remarkably stable for thousands of years, and the community is abundant enough to measure and culture. This is the first time scientists have successfully quantified fungal abundance this deep in the continental subsurface, and shown that complex eukaryotes can form a genuine ecosystem rather than just scattered, possibly dormant cells. Now let's step back from the microscopes and the wellheads for a moment. We have spent centuries telling ourselves a story about the limits of life. Life needs light, or at least the chemical leftovers of light. Life needs space, oxygen, moderate temperatures. The deep subsurface was supposed to be the realm of tough but simple prokaryotes, bacteria and archaea hanging on in the cracks. Complex cells with nuclei, multicellular animals, whole food webs, those belong to the sunlit world. This discovery does not overturn every assumption, but it punches a clean hole through one of the most comfortable ones. Under the right conditions, stable water, a long-term food source locked in rock, and enough time, eukaryotes can thrive in places we once wrote off as nearly sterile. The subsurface is not empty. It is simply very, very hard to sample without industrial equipment, and that raises a quieter, more unsettling question about carbon. About 90% of Earth's organic carbon is stored underground in coal, oil, and organic-rich rocks like the Antrim Shale. Climate models and carbon storage plans often treat that deep carbon as safely locked away. But if communities of fungi and their microbial partners are slowly converting pieces of it into gases, then the lock is not as tight as we thought. The carbon is biologically active. It is being eaten. The same logic applies to the carbon we plan to inject underground on purpose. Many carbon capture schemes end with pumping CO2 into the deep formations. We have barely begun to ask whether those formations already host organisms that might transform the carbon we bury there into something else, something that could eventually migrate or re-enter the atmosphere. There is also the simple matter of discovery itself. These wells have been producing gas for decades. We have been punching holes into this habitat, sometimes injecting biocides without ever knowing a novel fungal community and its tiny animal companions lived there. How many other such ecosystems exist in other shales, other fractured rocks, other continents? We may be underestimating global fungal diversity simply because we have never properly counted the subsurface. So here's the philosophical bite that stays with me. We keep finding life in places we once declared empty. The deep ocean, the dry valleys of Antarctica, the clouds, the rocks beneath our feet. Each time the map of the possible expands. And each time we are forced to admit that our previous map was drawn more from comfort than from evidence. The universe does not care about our categories of hospitable or inhospitable. It only cares what chemistry and time will allow. If complex life can persist for 11,000 years in a dark, salt-tinged fracture network hundreds of feet underground, feeding on rock that has been dead for 350 million years, then the boundary between the living and the merely chemical is thinner than we like to believe. Life is not a fragile visitor on a hostile planet. It is a patient, opportunistic process that will colonize any niche that offers a trickle of energy and a place to hide. That thought cuts two ways. On one side, it is hopeful. It suggests that if we ever look for life on Mars or the icy moons of Jupiter and Saturn, we should not limit ourselves to the sunlit or the recently wet. Ancient fractures, organic rich rocks, long isolated water, these may be the places where life, if it ever got started, still clings on. On the other side, it is humbling, even a little frightening. We are only beginning to inventory the life that already shares our own planet. Entire ecosystems exist beneath our feet that we have never named, never protected, and never considered when we make decisions about energy, carbon storage, or the long-term fate of the climate. We are altering habitats we did not know were there. The rock eaters of the Antrim Shale do not care about our philosophies. They will keep doing what they've done for millennia, quietly dissolving the ancient carbon around them, supporting their own small web of worms and water bears and parasites, indifferent to the surface world that only recently learned they exist. But we care, or at least we should, because every time we find life in a place we thought was empty, we are reminded that the universe is larger, stranger, and more crowded than our stories have allowed. The dark is not empty. It is simply waiting for someone to look carefully enough. That's it for today's bite. Hope you enjoyed the story. If you did, hit that subscribe button on your favorite podcast app. Give me a follow on social media. And until next time, stay strange and question everything.